So last lecture we were looking at the superposition of waves. We'll take it from that point onwards today. So we have so just doing a quick recap of what we discussed in the last lecture. So we're talking about transverse mechanical waves, waves on a string. And we discussed about the phasor diagram method of the net amplitude calculation for the case of interference. So we're talking about superposition of waves. In this, the first case of superposition we had seen was interference. We saw that waves propagating in the same direction and of same frequencies or we can say multiple waves of identical frequency traveling in the same direction on a string, superimpose or overlap to create the phenomena of interference. So if we had two waves of this type, what we saw is that their superposition, they are of common frequency. So both traveling along positive x-axis at speed v given by this. Okay, so their superposition becomes interference in this case. This results in some net amplitude so their superposition or interference that results in a net amplitude of a resultant wave of same frequency f and lambda given by this formula. So this is a brief recap of the last lecture's discussion. Yeah, Diti, unfortunately, actually, the last lecture was done live on a digital whiteboard, which had its own whiteboard software. So I don't have the notes of that. I will try to see if the notes were saved and send it to you. Okay, but otherwise you'll have to rely on the recording and make your notes from the recording. Just pause it at places, and make your notes from that. Anyhow, today we are doing questions based on this concept, so it will get clear once again. Okay. So then we had gone on to see that this net amplitude and the net phase constant can also be represented by a phasor diagram, which is basically like the vector triangle diagram. So it's very easy to remember and keep in mind. So today we will start with some application examples of this concept. So hopefully should be quite clear. Okay. So here, of course, phi is the phase difference. So they're traveling in the same direction with the same frequency, but they have a phase difference of phi. So we'll also understand how the phase difference comes as a result of various factors affecting the waves created by two different sources of same frequency on the string. Okay, so this set of formulae we can see can also be represented by what we call the phasor diagram, for the addition of the two waves which have a phase difference of phi but which have the common frequency. So their amplitudes can be represented by phasor arrows, just like vectors can be represented by vector arrows. And this sort of diagram can then represent this formula and this calculation above. So let's look at a quick numerical example with the application of this. Okay. So two waves of frequency 10 hertz each travel along the same direction on a string which has a tension of say 25 newtons and a linear mass density of 0.1 gram per centimeter. Okay. If their amplitudes are 1.2 millimeters and 1.6 millimeters, calculate the net amplitude from the interference or from the superposition So this is a direct type of question with the above application. If their phase difference is equal to pi by 2, 5 pi, 4 pi. pi by 3. Okay. So very straightforward question. Just you have to apply the above concept. Directly formula based type of question. So this is more of your simple JEE mains type of question, not anything with too much depth. So let's look at this question and its application first. Then we will come to understanding the relationship between phase difference and other factors in the system. But in this type of question, directly the phase difference is given. So you just plug it in the formula. Now, after having seen this, we had also seen the concept of constructive and destructive interference. So maximum possible amplitude is A1 plus A2. And that occurs when phi is of the type 2 and pi, where n is an integer. Whereas minimum possible amplitude we saw was the difference of the two. That happens when the phase difference is an odd multiple of pi. So this was constructive interference and this was destructive interference. These were two additional things that we discussed about. So you'll see that in the question I've given you, these two special cases are also covered. Okay, very good. Yes, that's correct. Yes, very good. Vashisht, your answers are correct. Yes, the last part, huh? Now it's correct. Okay, let's see. So in the A part, you can see that your net amplitude will become root of A1 square plus A2 square, because cos pi by 2 is 0. So it will become 2.0 millimeters. In the B part, you can see that the net amplitude will become the difference of the two amplitudes, which will become, much is it now? 0.4 millimeters, because cos 5 pi is the same thing as cos pi, is the same thing as minus 1. In the C part, the net amplitude will be the maximum amplitude case. So it will be 2.8 millimeters, because cos 4 pi is the same thing as cos 0, which is plus 1. The D part is the one where we have to do a bit of calculation. It's root of 1.2 square plus 1.6 square plus 2 into 1.2 into 1.6 into cos pi by 3, which is cos 60, is half. So we can take 0.4 common. So 3, 4 is 12. 0.4 into 25 plus 12, so 37. So 0.4 root 37 should be nearly, now root 37 we can write as square root of 36 plus 1, or 36 plus 1 to the power half. That is 6 into 1 plus. Okay, now people, let's move on to the next related concept, that phase difference phi in terms of path difference. So delta x and or time difference delta t. So I'll explain what these terms path difference and time difference mean. We'll understand this with examples. So next example, what is happening is we have an infinitely long string extending to infinity on this side. So this has a tension of 100 newtons, let's say, and a linear mass density of 0.1 grams per centimeter. Now what we're doing is at x equal to 0 and at x equal to d, we are attaching two simple harmonic oscillators which oscillate along the y-axis. So S1 and S2 are two simple harmonic oscillators of identical frequency, say 200 hertz. Or let's say the frequency is in fact 50 hertz. Now in the first case, S1 and S2 are synchronized and start simultaneously at t equal to 0. They have amplitudes E1 equal to 0.8 meters and E2 equal to 0.6 millimeters. Now D is given to us as half a meter or 50 centimeters. So what we want to do is write the equations of the individual waves created by S1 and S2. Find the phase difference between these waves and therefore find the net amplitude at a general point where x is greater than d. So we have a general point P like here, where x is equal to x greater than d. So at such a point, what is the net amplitude going to be? Okay. Now through this question, we will understand the relationship between phase difference and path difference. Because as the waves created by S1 and S2 are traveling to the point P, they are traveling different path lengths. Because one of them is located at x equal to 0. The other is not located at 0, but at some other coordinate x equal to d. So the waves are, so even though the two sources are synchronized and they are started simultaneously at t equal to 0, that means the sources are oscillating in phase, but the waves are not going to travel in phase because they have different path lengths that they are traveling. So through this question's calculation, we will understand the relationship between phase difference phi and path difference delta x, where delta x would be the difference in the path length traveled by the wave from S1 and S2 respectively to reach the point P. So just first find out all the parameters for the waves generated by S1 and S2, and from that we'll understand how to calculate the phase difference. So if you just follow the instructions of the questions up to the point where you write down the equations of the individual waves created by S1 and S2, you'll see the rest of it becomes quite natural to solve from there. So just try this out, people. Yeah, Tej, what I've written after individual waves is write the equations of the individual waves created by S1 and S2. Okay, the individual waves that are generated or created by the sources S1 and S2. Okay, so let's understand the individual sources. They are having a frequency of 50 hertz each. So omega will be 100 pi radians per second. And these values will create a wave speed also of 100 meters per second. So this frequency and this thing together will tell you that the wavelength will be 2 meters. So the angular wave number will be pi radians per meter. So now source S1 is A1 sine omega t and source S2 is A2 sine omega t, where omega for both of them is 100 pi and A1 and A2 are as given. So now if these are the individual sources, now you can see from the diagram that the sources are at different distances compared to the point P. So what will happen is that this is at x equal to 0 and this is at x equal to d. So at a general point like this, the wave created by the first source y1 will be equal to a1 sine omega t minus kx, where now k is omega by v or this much. Whereas the wave created by the second source, so that's y2. Now that's only traveling a distance of x minus d, whereas this is traveling a distance of x. So this is at x equal to x. Okay, so from S1, this is the equation. Similarly, from S2, so the sources are synchronized as you can see, but the waves are not because there is a path difference. Okay, so you can see that where this phi is actually kd. So here d is the path difference delta x. Okay, so the phase difference created by the path difference is 2 pi by lambda into delta x. So here it is pi into, now d was given to us as 50 centimeters. In this case, the phase difference because of this becomes pi by 2. Okay, so this is how in this question you are meant to understand it logically, that how we calculate the phase difference in terms of path difference. So Ansh, you wanted me to scroll up to the question or this part? Okay. Right, so that is done. Now we move on to a second part of this question where we'll see that how to adjust the phase difference if the sources are not synchronized. Okay, so second part of the question, everything else remains the same. Okay, so both S1 and S2 again have a common frequency of 50 hertz. Okay, and they have these kind of amplitudes 0.8. Achha, let's first discuss the net amplitude in this case. I'll come to the second part. We have to do the main part of the question. We've calculated the phase difference, but now about the net amplitude. So now you can see that we are therefore at point P, x equal to x. The resultant wave is the interference of these two. Okay. Where phi after the calculation comes out to be pi by 2. Okay. So that means the net amplitude is going to be square root of a1 square plus a2 square, which in the phasor diagram will look like this. Okay. Phi is pi by 2. So our net amplitude, when we calculate it, you'll see it comes out to be 1 millimeter. So this is 0.8 and this is 0.6 millimeters. When we calculate this, this will come out to be 1 millimeter. This phase angle will come out to be 37 degrees. So this Y net will become say like this, where the net amplitude is 1 millimeter, omega is 100 pi, k is pi radians per meter, and this epsilon is 37 degrees, the net phase. Okay, so that's the conclusion of the first part. Now, second part, both S1 and S2 are again common frequency this much and amplitudes like this. Okay, and same thing, tension in the string is 100 newtons, linear mass density is 0.1 gram per centimeter. So all these are the same, but now D is 1.5 meters or 150 centimeters. Okay, so and the source S1 is started at a delayed time of delta t equal to um, five milliseconds compared to S2, which is started at t equal to 0. So again, what we have to do is write equations of the individual waves from S1 and S2. Okay, then calculate the phase difference between them. And then from that, calculate the net amplitude. Okay, people, let's understand this in detail now. So what is happening is that the first source is not starting at t equal to 0. It is starting with a delay. So it will have an equation of oscillation like this. So the wave it produces, now that's traveling a distance x again. So the source S1 is located at x equal to 0, but it starts at t equal to delta t. And the source S2 is located at x equal to t, but starts at t equal to 0. Both are of same frequency f and of amplitudes A1 and A2. So at a general point like this, where x is greater than d, the first one will create a wave given by the equation A1 sine omega into t minus delta t minus kx, because the wave is traveling a distance x. Or we can write this as A1 sine omega t minus kx minus alpha, let's say, where alpha is omega delta t. Okay. So that alpha here becomes, so omega is 2 pi f, so once again it's 100 pi, and delta t this time is 5 milliseconds. So this omega delta t becomes 100 pi into 5 into 10 raised power minus 3. So you can see it becomes 0.5 pi. Pi by 2. Okay. Whereas the second source, it started at t equal to 0. So the source will oscillate according to this equation. But the wave from it travels a distance which is x minus d. So it is omega t minus k into x minus d. Or we can write it as a2 sine omega t minus kx plus beta, let's say, where beta is a constant. So here we can see that beta is kd. Okay, this kind of thing. So it is wavelength we had seen was 2 meters. Okay, and this time this is 1.5. So this is 3 pi by 2. So beta is 3 pi by 2, whereas alpha is pi by 2. So we can see that y1 is a1 sine omega t minus kx minus pi by 2, and y2 is a2 sine omega t minus kx plus 3 pi by 2. So these are the two waves that we are adding now. So you can see that the phase difference between them is how much now? How much is the phase difference? It's the difference of these two terms, na? This whole term minus this whole term, that is the phase difference. So the phase difference is actually 3 pi by 2 minus of minus pi by 2. Okay. In other words, it's becoming alpha plus beta. So it's 2 pi. So interestingly, this will result in constructive interference. So in this case, what we are seeing is that the phase difference is coming out to be 2 pi by lambda delta x plus 2 pi f delta t. So it is coming out to be the sum of two terms, because the wave which is traveling a longer distance, that one is delayed. So the two effects are adding to give phase difference. See, the wave from S1 is traveling for a longer time. I mean, it's traveling through a longer distance, and plus it is delayed because the start of S1 is delayed. So that's why the two effects of delta x and delta t, they're adding to each other. Okay. Okay, so their superposition now will result in constructive interference, so the net amplitude will add up. Okay, so in this case, what will happen? The net amplitude will become A1 plus A because of this 2 pi. 1.4 millimeters. Now, coincidentally, you can also understand that suppose S2 was given the delay compared to S1, then the net phase difference would have been KD minus omega delta T instead of being KD plus. Here the phase difference is KD plus omega delta T, because the wave that is having to travel longer distance is also delayed in time. The two effects are adding. So hope this concept is clear here, which you can see from the way we framed the equations also. But suppose S2 was given a delay instead of S1, then Y1 would be omega T minus Kx, but Y2 would be omega into T minus delta T minus K into X minus D. So the phase difference would have become KD minus omega delta T. Instead of KD plus omega delta T, it would have become. So that is how these two things are interrelated. Okay, so that's an important concept here. Because the phase difference is 2 pi na beta. So the two waves which are overlapping are in phase now. So the resultant wave will also be, visualize the phasor diagram. Yeah, this part, Diti, I've explained this over here, that you can see the source from which the wave is traveling a distance x is given a delay compared to the source from which this is given x minus d. So the wave that is traveling a longer distance is also delayed in time. So that is why the two effects of delta t and delta x are adding to give a net phase difference, which is the sum of these two. Anyway, the wave from S1 will take longer to reach the point P, and plus you're delaying the source by starting it at a later time of delta t. That's why the net phase difference is becoming the sum of these two terms. Is it clear now, Diti? Okay, very good. Okay. So same thing, suppose what we have done is that, suppose once again D is 1.5 meters and common frequency is 50 hertz and all that, wave speed is 100 meters per second. All these things are same, but now S2 is delayed and started at that same delta t equal to, let's say, 5 milliseconds. Okay, and S1 is started at t equal to 0. So now what would happen is our S1's equation would be A1 sine omega t, but our source S2 would oscillate according to this equation, like this. Okay, so correspondingly, the wave created by S1 and the wave created by S2, they would overlap in a different way over here, because the phase difference will come out to be, so this is started at t equal to 0 from x equal to 0. This is started at a delay of delta t, but from x equal to d. And at a point P like this, where x is greater than d, this one would create the equation or the wave A1 sine omega t minus kx. This would create the wave equation t minus delta t x minus d. So you can see that here the phase difference would become different. Here phi would be kd minus omega delta t. That is 2 pi by lambda into that path difference minus 2 pi f into the time difference. So this would again come out to be 3 pi by 2, but this time minus pi by 2. This would be pi. So in this case, we would have destructive interference. Net amplitude come out to be 0.2 millimeters. Okay, just take down this part, then I'll scroll back to the earlier part also. Okay, people, I'm scrolling up to the earlier part also once. Make sure you note that down. So now, once again, you'll understand why in this case, the two terms were adding up for the phase difference, and whereas in the third case that I've shown you, the two terms are subtracting. Because a wave that is traveling a longer distance is also given a delayed time in second part, whereas the wave that is traveling the longer distance, that is started at t equal to 0, and the other one is given the delay. So it brings the phase difference, it makes the phase difference less in the third case. Okay, so let's move on to the next part of superposition of waves now. So with these examples, we understood all aspects about interference, okay, especially how to calculate the phase difference in terms of path difference and time difference. That is the more tricky thing. Okay, and this will come very useful in future chapters like sound and light waves also. The same type of concepts we'll be using. Now coming back to superposition in general, superposition of waves in general. Now we look at the second category of superposition, which is called standing or stationary waves. Now these are created when waves traveling in opposite directions. So again, remember we are talking about transverse 1D harmonic waves. Okay. The physical example being waves on a string. So these are created when waves of identical frequency, like interference, here also frequency needs to be identical, but also in this case amplitude. The interference amplitudes could have been different, but here identical frequency and amplitude traveling in opposite directions. So this is how this is different. In interference, they should be traveling in the same direction. Here they are traveling in opposite directions. Okay, these kind of things superimpose to create standing waves, or these are also called stationary waves. So let's say we have got this long string. Now on this, from one side there is one source that is generated and creating waves like this. And on the other side, the waves are traveling in the opposite direction, but both are of same frequency and amplitude. Okay, so y1 would be, let's say, of the type A sine omega t minus kx. We'll keep the phase constant 0 just for mathematical simplicity initially, and then I'll tell you what happens if we have some general phase constants. So this second wave will be omega t plus kx. It's traveling in the opposite direction. Okay, this is traveling along the negative x-axis. This is traveling at b equal to omega by k along positive x-axis, the first one. So the sign is minus omega t minus kx, whereas the second one is traveling at the same v equal to omega by k, but along the negative x-axis, because the sign between omega t and kx in the bracket is positive. Okay, so when these superimpose at some general x equal to x, so superposition of y1 and y2, this creates a net effect which we can solve very simply by just using the sin A plus sin B formula. Okay. Now we just use this familiar formula from trigonometry, 2 sin A plus B by 2 cos B is larger than A, then B minus A by 2. If A is larger than B, then it is A minus B by 2. So just apply this formula over here. So this becomes 2 times sine of this term plus this term by 2. So that will become sine omega t into cos of this term minus this term by this. So this will become by 2. That will become cos kx. So as you can see, this is no longer the equation of a traveling wave. This is the equation of a wave which is of a different type. Hence, we call it a standing wave because it's not a traveling pattern. And why it's not a traveling pattern, I'll just explain in a moment. Okay. So I'm just reordering the terms. Okay, I'm putting cos kx first and sine omega t in the end. But you can understand here that this does not represent a traveling wave, because the argument of the function is not of the type omega t plus or minus kx. So it turns out that the effect of superposing two such waves of same frequency and amplitude but traveling in opposite directions, it creates some other type of disturbance in the string, not a traveling pattern, not a traveling sine wave, unlike interference, where the resultant effect is still a traveling sine wave. So just make a note up to here, then we'll discuss further about this. So this equation that we've written in the end, the boxed one, that only is called the general equation of a standing or a stationary wave, and we'll discuss more about it. Now let's understand the interpretation of this equation. So in this equation, what you can see that what it represents is that it represents an equation such that y is a function of x and t such that all the medium particles are in SHM. Okay, that sine omega t term that is showing you that they are in SHM. Okay, but with amplitude which depend on position. So time varying position dependent amplitude. So in this equation, we can think of this term like an amplitude, and this is the harmonic motion. So amplitude at any point x equal to x on the string is 2a cos kx. Okay, and frequency of oscillation is equal to omega by 2 pi, or time period of oscillation is 2 pi by omega. So that is why if you look at this equation, and you plot it at various different times, equation, if you plot it at various different times, for example, at t equal to 0, it just becomes 0. Okay. At t equal to 1/8 of the time period, where time period is this, what happens is the sine omega t term becomes 1 by root 2. So this becomes root 2a cos kx. At t equal to t by 4, that sine omega t term becomes sine pi by 2. So it becomes 1. So it becomes 2a cos kx. Then for example, at t equal to 3t by 8, again it becomes root 2a cos kx, like this. So if we plot the snapshot picture at various different times, y versus x, we'll see, for example, that at t equal to 0, look like this, but at certain time, the shape of the string is like this. So this is root 2a. Then at a later time, it becomes like this. That t equal to t by 4. Okay, and then still later, it will become something like this. So all the medium particles are doing SHM, but depending on where they are located, they have different amplitudes. You can see that these particles here, they're having maximum amplitude, and these particles here, they're having zero amplitude. They're not oscillating. That is why it is called a stationary wave pattern or a standing wave. Just note down this additional information.
Sir, can you scroll up a little?
Okay, Diti, I'll scroll up. So with this, we complete today's session. Okay, next time we will look at more examples, numerical applications of standing waves. And with that, we will then move on to sound, which is the next chapter in wave mechanics. We're done with the theory part of this thing. We are done with the theory part of transverse waves, or the first chapter of sound, the first chapter of waves. So that's it for today's session, people. You can just finish noting this down if you're writing down. Otherwise, we are done with the session. Have a nice day.
Bye, sir. Thank you, sir.